Feel. Video stand
So let us begin already 15 minutes call. We will be very brief and we'll finish it as quickly as we can. That semi-market process that we are actually covering, it is very similar to a market process, only difference is that time between conditions actually have a distribution. That is, we call it general distribution. Any distribution can be used. We have discussed all of this in the last class. Now, for the discrete and semi-market process, actually we are focusing on two important components of the process. One is the embedded market chip that actually is associated with the market process. And we will also discuss this embedded market chip in the last class. And another one is the holding time of the process in the probability model that actually are associated with this semi-market process include number one is the transition probability matrix of the embedded market chain. Let's say this matrix is E. This we have the holding time distribution. Holding time distribution, actually we have two holding times. One is the holding time in state I, another one is the holding time of the process when the process actually in the next temperature goes from I to state J. So when we consider the holding time of I is, we can denote by A sub I, and the holding time of the process when the next state of the process in J is or can be denoted by A Ij. So we need the distribution of both the two quantities. One is P sub A psi. Since it's a discrete time semi-market process, both A psi and A Ij are discrete random variable. Let's say the values are M. So these two are the distribution of the holding times. Then actually we need to consider the long-term probability or the limiting probability. Which we are very familiar with, pi 1, pi 2. Pi n. Then finally, long-term proportion of time. Now, there is a question. If we are considering a pure Markov chain, DTLC, what is the proportion of time in the long run that the process will be easy to die?
Pi I.
Sorry?
Pi I.
That what is the frequency that the process will be easy to die?
Pi I.
There are two quantities, sir. One is the, in the long run, the frequency of visiting is 10 I. That means if there are in the long run, there are 1 million or 1 million transistors, how many transitions, how many times process will visit state I, right? Or the process will leave a state I. Visiting state I and leaving state I are same. But one is the frequency, another quantity is what? Duration. If we consider the process is running for 1 million years, what is the proportion of time the process will be in state I? This is the total amount of time the process will be in state, or the fraction of time that the process will be in state I. These two quantities, when I ask you proportion of time, you said that pi I represents the duration. When I ask what is the frequency, is it correct? Each time the process visit state I, it will stay here for 1. Right? 1 time slot. That's why when we calculate the fraction, the frequency and duration actually are values will be different. But when you consider the fraction of frequency of the visiting is one thing, and the proportion of time, this is in terms of if you measure the duration, that will have different value. But when you are considering the fraction of time it will visit, then both of these two quantities actually are represented by pi. Now, when you consider Pn, the long-term probability of the CTN, what is the fraction of time the process will be in state N? Is it also true for CTN? In fact, that means the long-term probabilities, Pn or Pi, whatever we call it, actually according to the text we call it pi I for the leniency and Pn for the secrecy, and they are representing both the frequency of visiting a particular state as well as the fraction of time the process will be in a particular state. And this is due to the numberless property and the exponential distribution. Right? However, when we are in a semi-Markov model, the fraction, the frequency that is defined by pi 1, pi 2, and pi n, and the duration of the fraction of time, they are not same because it has a different distribution. We can consider consider an arbitrary Markov chain. Let's say it represents the up and down time of a machine. And the conditions are very simple. What? From up it goes to down, and from down when it is repaired it goes to. Let's say average uptime is 100 hours. And average repair time is 10 hours. What is the long-term probability here? Pi 1 or pi up and pi down? Is pi up and pi down now only representing the frequency of visiting? And is it this? What is the condition probability matrix? Yes. Is this a doubly stochastic matrix? Rows are sum to 1. So pi 1 is pi 2 is. And actually it is rational. Why is it rational? Every time it goes to down state, what is the next state? So there will be equal number of up and down state transitions, right? Because every up state actually eventually leads to a down state, and every down state actually will actually after equally already element of the machine, the process will move on to the. That's why Now can we say the long-term proportion of time the process will visit up? No, because once it goes to the upper state, it remains there 100 hours on an average, and 10 repair time if we multiply, then this becomes. So what is the fraction of time the machine will be in upper state? How can we calculate? In the long run, what is the time that the process will be in upper state? Half into 100, right?
Height.
And this is half into. And this is what? This is. So what is the portion of time the machine will be in the upper state? On an average, out of every 55 hours, the machine will be in the upper state for 50 hours, and it will be in the downward state for. And this is rational, you can say. You can consider a cycle of 110 hours. Sorry, my mistake. Out of this 110 hours, 100 hours will be here, up, and the 10 hours will be down. Then again 100 hours up, then up. Every 110 hours, the machine will be up in the, machine will be in the upper state for 100 hours and down state in the, because, any questions?
No, sir.
Then whom are you pointing to? Wait. It is not that much important, because that very gentleman, where is he? Elsek. Where is he? Even I do not know, or I did not know that he is one of my students. He already participated in one course. Almost at the halfway of another course. I actually encountered him for the first time in the exam. So, attendance is CGPA matters. Attendance. So, from here, our objective is what? We need to find out the embedded Markov chain. Once we have the embedded Markov chain, we need to find out the transition probability matrix. We need to find out the holding time distributions, then the long-term probability vector, and finally the long-term proportion. Then actually any analysis of a semi-Markov process is done. There is one more quantity. First, passage time. Today we will consider the next one. Now, when you are given a semi-Markov process, what are you given? Can anyone tell? What are you given? Okay. You are given a diagram like this. What is it? It says what are the states of the Markov chain. And we assume that it's a finite state Markov chain. That means number of states are. And then from each state to any other states, the probability of transition is given. Given the probability of the state transition, if there is any. Right? And once you know the probability of transition for all the states to any other states, then what you can actually extract from here, the embedded Markov chain. What is the difference between this diagram and an embedded Markov chain? In case of an embedded Markov chain, we do not need we do not need the distribution of the time. As we mentioned, in case of an embedded Markov chain, we only consider the transitions between states and ignore the times between transitions. So once we actually ignore the times between the states, then we can easily extract one quantity. What is that? The transition probability. That means we know the probability from probability of transition for any state I to J, and we can have the transition probability. Say this is P1, 1, 2. This is P1, P2, P1, P. Right. So the main thing that the transition probability matrix can be extracted once we know the embedded architecture. And then our job is to calculate the limiting probability vector process. How can we calculate this limiting probability vector? By finding the system of linear equations, which is pi j equal to any volunteer? For all state I equal to 1 to n, pi I times the probability of transition from I to J. And actually, the normalization condition, this is so this the system of linear equations. How many equations are here? If we solve the system of linear equation, then we can find the values of these vectors, right? But there is one condition. What is the condition? The embedded Markov chain has to be R1. When do we say a Markov chain is R1? If it has a single class. What does we mean by the term single class? All states
Communicate.
right? It has to be irreducible. Actually, when all states communicate, it is irreducible. But there is a condition that even though all states communicate as a single class, it might not be orthogonal. What is the additional condition here?
Positive recurrent.
Positive. The positive recurrent is inside this one. Actually, it has to be a theory. For example, if I could take something like this, not this one. It will never actually converge. It is right? Because always from 0 it goes to 1, from 1 to it goes to 2, from 2 it goes to 3, and the probabilities will remain 1, 1, 1. It will never converge, right? Rows will never be identical. So what we need the discrete time Markov chain is harmonic. That means it has a single class. Okay, positive recurrent. All states communicate. It is irreducible, and eventually states are a priori. Then we can solve the system of linear equation, and the solution to the system of linear equation will give us the long-term probability equation. Now, when we move from the embedded Markov chain to holding times, we consider there are two types of holding times, as we already mentioned. The holding time, one actually is considered the holding time of the state I. We do not consider what is the next state of the process. And another case, the holding time is considered with the next state in. If the next state is defined. In fact, this one is dependent on this one. We can, if we just see the definition, each time the process visits states I, it chooses the next step first. It is right. It chooses the next step first. Then it spends a random time depending on J. So whenever the process will move on to step I, then it will decide what will be the next step. Okay, it is J. Then the distribution of J is given from there, actually it will find a time and it will stay there. It is not the fact that the process can arbitrarily identify the amount of time it will stay state I, then it will move on to the state J. So first it has to choose the next state. The next state is chosen first, then the random time. So we have two holding times. One is Ij. The holding time in state I when the next system it is already known that the process will proceed, and the distribution of this one is Ij with values m will be probability that is Ij equal to m, given that xn is equal to I and xn plus 1 equal to and n equal to 1 and so on. So what does this mean? It means that if the current state of the process is I and the next state is j, only then the holding time is n. And we want to know the probability of this. The probability that the holding time is m when the current state is I here and the next state is j. So once we have this one, what we can calculate? We can calculate the expected value. What is the expected value? For all values of n equal to 1 to infinity, m will be multiplied by the BMF of a size of right? And also what we need, this expected value should be less than infinity. In many cases, we also denote this one by V1. The average amount of time that the process stays in state I, when actually the transition from I will be occurred to state. Then the distribution of already I have written this one. Now the distribution of A side. What is A side? A side actually the holding time what does it mean? Asia is the holding time in state I, and the PMF of ace I is the probability that ace I is good.
J hasn't been selected yet.
Sorry?
J hasn't been selected yet.
No, J has been selected. If J has been selected, then how can we include J? That's the question.
J equals I.
That means, say there are two states. From I, say from state A, you can go to state 1. Or simply you can write this from 1, you can go to either state 2 or state 3. Now, when you go to state 2, what is the probability that the holding time is, say 2, is E is 1 to 2, right? And then when you move from 1 to 3, the holding time is probability that the holding time is, sorry, third bracket will not be there, is 1, 3. want to know the holding time of I it will be the holding time of this one average. How do we average this one? We average this as what is the probability that a move is from 1 to t? What is the probability that it moves from 1? So, and by applying what rule? It will be P12 times probability that H12 for 2 plus P13 times probability that H13 for 2. So when we average this one, we call it actually by applying the sum rule. By applying the sum rule of probability, ricochet. By applying the sum rule of probability, what we do, we actually write here, it is the, for all states, j equal to 1 to n, the probability that the process will go from I to j. And when it goes to I to j, then the probability that it has a delay of. If you sum it for all states, then actually it gets to the average of the probabilities. And the summation actually eventually told you the probability, the holding time at process of the process in state 1 for the value and the generalization. Right. Is this clear? And once you have the PMF, then what you can calculate? You can calculate the expected value of, right, like this one. We calculate the expected value. What will be the expected value here? For all values of m, you can calculate the holding time. And now, what you do for m equal to 1 to infinity, m times the PMF of inside for the value of m. If you do it, then you can calculate the holding time for a step. Now it's a two-step process. What is two-step? In the first step, you have to calculate these PMF. Then in the second step, you have to calculate the PMF. And then you need to calculate the expected. উপরে উঠে গেল কোন হচ্ছে একটু?
স্যার আরেকবার একটু দেখুন।
ঠিক জায়গায় আসে। Okay. So, but there is other way around. If you already calculated the expected value of this one, or mu I say, if it is already calculated or given, then by applying the law of total expectation, what we can calculate? And this is the better way, because in many cases, here, instead of this distribution, you might be mu2 or s to expected value. So if the expected value is already given, then actually you can apply the law of product expectation. So you can apply the law of product expectation to calculate the expected value. Right? Now we have the chain, we have the probability matrix, we have the delay distributions. Now what are our next steps? Our next step is very simple. We want to know the long-term behavior. And the long-term behavior has two parts, as we already have discussed. One is the long-term probability of visiting state I, that is P pi I, and the long-term fraction of time staying in state I, which we will denote as pi I. Calculating this one, we have already seen, right? By solve the system of linear equation, you will get pi I. So, solving the system of linear equation, we will get the pi. এখানে লেখা আরেকখানে নিয়ে বসে রেখেছে কেন করতেছি জানো যে কিছুদিন পরেই বলবে যে পেইড ভার্সন Anyway, long-term probability of visiting state I and the long-term fraction of that. Now, we already have calculated this one. So our next job is to find this one. To find this one, as I already mentioned, that in case of a DTNC or CTNC, PIN or PN, they both what? Long-term frequency and the long-term duration. But for this one, for the semi-quantum chain, it just tells the frequency and phi I tells the frequency long-term and duration long-term. Right? So, how can we calculate this? This one, in the book you will find a Nicolas mathematics. Our job is not to do that. We want to calculate this one intuitively. How? They also use this, but we will actually ignore the math. Just go to the point where we can actually find the rationale behind the final formulation. This semi-quantum process has a relation to the renewal reward process. What is that? Let's say this time the process visit state I, a renewal occur. Right? Whenever the process will be visiting state I, renewal occurs. Starting from the first one. Like for simplicity, we assume the process starts in state I. Every time it will go to state I, renewal. Again it will stay, it will go to state I, another renewal. Every time a renewal occurs, is renewal results in a reward. Previously, we considered the reward is the money, right? For example, in case of a light bulb, we have the example that cost is the reward and this is the agreement. For now, let us consider the reward So the reward is the holding time in state I. Then, in the renewal reward theorem, it is here, right somewhere. What is the renewal? The reward, it should be renewal theorem. What is the equation? The renewal rate was defined in such a way that actually if in the first renewal cycle, renewal time, you get the reward U1, then we define this, the renewal rate is expected value of Y1 divided by the expected value of X1. Even whenever a renewal occurs, we define it as a cycle. And the long-term average reward is defined as the what? expected reward in a cycle? Divided by
cycle length.
Right. So if we can define a cycle, what we are considering, whenever a renewal occurs, cycle finish or start, either way we can consider it. Right? So from here, visiting state I and then visiting state I. This is a cycle, right? If this is a cycle starting from here, this one, before it goes to state I, then what is the reward that we defined? The time that the process stays in state I. What is this? Is this clear? This is the cycle and this is the reward. Is the question clear or not? This is the cycle length. Starting from I, just before I. So the process was in a state I here, and just before going to the state I, you can consider. Or after leaving here, just it enters I, is fine. And the amount of time the process will be in a state I is this one. Because in between, here to here, the process never entered into a state I. So the reward is this one. Now, what is the cycle length? In the long run. Can you do it? What is the cycle length? Okay. What is the reward? What is the fraction of time the process will be visit in a state I? The fraction of time in the long run, the process will visit a state I is what? And each time the process visits I, what is the average amount of time the process will stay in state I? So what is this one? In the long run, the amount of time the process will be in state. And what is the cycle length with this system? In the long run, total amount of time the process will be in state I, j, k1. In the first process, pi 1, mu 1 plus pi 2, mu 2 plus pi n, mu n. And here it will be pi n, mu n. So, this is the average reward. Is this clear? And here average, long-term average reward is what? Fraction of time the process is in state I. So, what we can do, this renewal reward, actually this phi I, will be the expected reward for state I divided by expected cycle. So here I should write in a better way. Expected reward in a cycle, then the cycle. Now, if we calculate the phi I, then we can see. Let's say the cycle length is t now. T. What is phi I? Sorry, phi I. Fraction of time the process, the frequency of visiting a state. And if we multiply this one with t, and then multiply with mu1, then actually it gives us the fraction of time the process will take. And then actually this phi I can be considered as pi I divided times mu I divided by for all j pi I by mu I. So this is the here as we mentioned that this one is pi I from the solution of the system of linear equations, and once we have the system of linear equations, then we need another quantity which is pi I, the average holding time in state I, to calculate the fraction of time. Actually, this is the total time that the process will be in all states, and this is the fraction of time the process will be in state I. That's why this ratio is giving us the. We do not need to go through all such equations. We can, but this is one space of time. Now we will see an example. And this example will finish this class. Okay. The example is a very simple one. And ChatGPT was asked to give a simple example. And it produces this one. I think when I will ask for a complex one, what are the state of the semi-Markov process? R1, 2, 3. This is 1, this is 2, and this is 3. From state 1, the process can only go to state 2. And what is the probability then? 1. And instead of the holding time distribution from 1 to 2, what it gives that mu1 is equal to 4. From state 2, the process can go to state 1 or it can go to state 3. This occurs with probability half and this occurs with probability half. And then the average holding time from 2 to 1 is also not also is 2. Average holding time from 2 to 3 is 6. And now the final one, the process moves on to state 1 only from state 3, and the probability is 1, and the average holding time from 3 to 1 is 3. Now, from this process, if we just consider the transition probabilities and ignore what? The holding time, then we have a embedded Markov chain like this. Probability is 1, probability is half, probability is half, and probability is look at the transition probability matrix from 1 to 1 the probability is 0, 1 to 2 the probability is 1, 1 to 3 probability is 0. For step 2, 2 to 1 is half, 2 to 3 is half, 2 to 2 is 0, and from 3 only probability which is non-zero is 0, 3 to 1. This is clear. Now, this is an algorithm Markov chain. All states communicate. Yes, from 1 we can go to 2, from 1 we can go to 2 and then 3. So from 1 we can go to 3. From 2 we can go to 1, from 2 we can go to 3. From 2 to 3 we can go to 1, and from 3 we can go to 2 by. So all states are recurrent, they are periodic, and chain is harmonic. So we can solve the system of linear equation. What is the system of linear equation? Pi 1 equal to what? Half into pi 2, right? Plus pi 2. So when we will be writing pi 1, then we will be focusing on only first column. Pi 1 will be multiplied with this probability 0, pi 2 will be multiplied by half, pi 3 will be multiplied by 1. For pi 2, our focus will be this one, and it is pi 1. For pi 3, we are here, it is equal to half into pi 2. And finally, the normalization condition says pi 1 plus pi 2 plus pi 3 equal to what? 1. Then pi 1 can be replaced by pi 2, pi 2 remains, and pi 3 can be replaced by half pi 2. Then in the left hand side, how many pi 2s are here?
1
5 by 2 divided by 2 equal to 1. So pi 2 equal to 2 by 5 equal to pi 1. And so pi 3 equal to
2 by 10.
Next one, it is given that mu 1 2 equal to what? 4. Mu 2 1 equal to 2. Mu 2 3 equal to 6. And mu 3 1 equal to 3. Right? Just check here. Mu 1 to 2 is 4. Then mu 2 to 1 is 2. Mu 2 to 3 is 6 and mu 3 to 1 is. Then what is the value of mu 1?
4.
Mu 1 is, if we write, okay, let us first write this one. Mu I is what? For j equal to 1 to 3.
Probability.
Mu ij. That's not right. We wrote the probability first. Ij times from state 1, we can only go to state. So mu 1 is equal to, probability is 1 times mu 1 2, this is okay. 1 2. This will be 1 times 4 equal to 4. Then mu 2 equal to, from state 2, we can go to 1 or we can go to 3. We can go to 1 with probability half, we can go to 3 with probability. So it will be half into 2 plus half into which will be 4. And mu 3 equal to
3.
1 into 3 equal to, right? Then next remaining thing is phi 1. Phi 1 is what? Phi 1 mu 1 divided by phi 1 mu 1 plus phi 2 mu 2 plus phi 3. Right? And what are the values? Phi 1 is what? 2 by 5. Mu 1 is, so 2 by 5 into 4 plus 2 by 5 into 4 plus 1 by 5 into 3. The values are from here. Pi 1 is 4, pi 2 is 4, and pi 3 is 3. So 4, 4, 6. And probabilities are 2 by 5, 2 by 5, and 1 by 5. Then we have 8 by 5. Underneath 8 plus 8, 16, 9. 9. Right? And phi 2? Phi 2 is 2 by 5 into 4. And underneath we have the same thing, 5 equal to what? 8 by 9. Phi 3 is 1 by 5 into 3, 19 by 5. This is 3 by 2. So, in a cycle of 19 units, the process will be in state I for 8 units. 8 units of time in phi 2, step 2, 8 units of time, and in step 2. So 8 plus 8 plus 3. So two things actually we identify here. One is The pi only defines the frequency of visiting a state I. It does not tell about the duration, fraction of time process will be in state I. And to calculate that one, what we need to calculate is phi 1, phi 2, phi 3. We are considering this another way. Before we finish the chapter, actually, I'll finish it quickly in 1 or 2 minutes. The state 1, 2, 3 actually are the states of a continuous time Markov chain, which is semi-Markov process. Continuous time semi-Markov process. Only difference between this one and discrete time is that. What is the difference? In case of discrete time, it was since the time is continuous now, we need a continuous random variable, and so when we consider the discrete time semi-Markov chain, it was, and when we will extract the embedded Markov chain, we will ignore the time, whether it is a continuous time or discrete time semi-Markov process, there is no difference. The embedded Markov chains are same for both, but the calculation of mu1 and mu1 actually are different. Markov chain, we use summation. For a continuous Markov, continuous distribution, we have to use is this clear? So we finish here.